welcome everyone. Thank you for coming to this talk today. So it's my great pleasure to introduce Andreas Malikopoulos. We joined Cornell recently in the fall, I guess this fall. So he's in the Civil and Environmental Engineering department. He's also affiliated with System Engineering. So Andrea did his bachelor in Greece, in National Technical University of Athens, and then he did his master and PhD at the University of Michigan, everything in mechanical engineering. And then for a little while, he joined General Motors Global Research and Development Team, and then Oak Ridge National Laboratory, before becoming a professor at the University of Delaware, and then finally joining us here at Cornell. So his research interests are very broad. They span different areas, including analysis, optimization, control of cyber-physical systems. He's also done some work on decentralized stochastic system and learning in complex systems. And of course, he's won a number of awards for his research, including the Dare to Dream Opportunity Grant for University of Michigan, the 2019 IEEE Intelligent Transportation System Young Research Award, and the 2020 University of Delaware College of Engineering Outstanding Junior Faculty Award. He's also been selected as a 2012 Kavli Frontier of Science Scholar by the National Academy of Science. So having said that, it's a great pleasure to have you here. And
thank you, Francesca. Thank you for the invitation. Thank you all for coming on a Friday nice afternoon in the fall. So today I'll try to provide some challenges on learning and control in engineering systems, and then at the end I will try to make the case that if we can combine learning and control in some particular applications, we might be better off. So our world is changing, and one particular sector that undergoes significant transformation is transportation. We're about to transform from typical conventional vehicles with internal combustion engines and move on to completely electric vehicles. And with this transformation, we have several opportunities and challenges. For example, we have the opportunities to upgrade our existing infrastructure, transportation infrastructure, and enhance it with fast charging stations that can fast charge the electric vehicles. We have opportunities to develop control technologies that can help us manipulate the increasing electricity demand from electric vehicles and sort of try to optimize this demand in a way to avoid overloading the grid. We have opportunities to integrate the vehicles with the commercial or residential buildings and eventually create off-grid buildings. With the introduction of connected and automated vehicles, we can share information from the vehicles and do better controls to optimize transportation efficiency and also, of course, safety. If you look at all these applications, there is a common theme. We have some cyber component information or data that we use to control the physical entities. So we typically address cyber-physical systems. Now, you might ask me, why do I focus so much on transportation? Well, in 2017, the United States consumed, on average, 19.6 million barrels of petroleum on a daily basis, and transportation accounted for 71% of that usage. If you think about it, this usage is enough to fill up the Empire State Building 2 times per day just to propel vehicles. So you can see that the impact of transportation in energy is significant. So with the introduction of connected automated vehicles, we have several opportunities to improve the energy transportation efficiency and also improve safety overall. So what I plan to do today is I will show you some case studies that span learning for CPS, and in particular in advanced propulsion systems, some model-based control approaches in connected automated vehicles. And through these case studies that I have the chance to work in the past, I will try to highlight the challenges and opportunities in learning and control. And at the end, I will try to convince you that if we can combine the learning and control tasks in specific applications, under the CPS domain, we might be better off. Before I get started, let me introduce you and acknowledge the contribution of my students in the IDS lab. In the IDS lab, we develop theories and algorithms that can help us, make the cyber-physical systems able to realize their optimal operation while interacting with the environment. The focus of our research is mainly on emerging mobility systems, smart cities. To validate some of our approaches, we have built a scale smart city which covers 20 by 20 feet. This is being rebuilt as we speak in the Hollister Hall, so it should be ready in about a month or so. In this city, we have about 50 robotic cars that we can use to prove some concepts in transportation. These cars are on a scale 1 to 25. So we can use these cars to validate the control approaches that we develop. We can prove some newly introduced approaches like having drones collaborating with ground vehicles in specific scenarios of first last mile delivery in Amazon case. Like you can see here, the drone supposed to pick up a package from the building and then will coordinate with a car to drop off the package. We can use this to show how we can use drones as coordinations to collect information from the transportation and then pass this information back to the vehicles in order to improve efficiency. As you can see here, in this case, the coordinator selects information from the vehicles and the vehicles can cross the intersection without stop-and-go driving. So we use this testbed to do those kinds of experiments in a safe environment. We can also develop, we have integrate one driver emulator into the robotic cars, so we can drive the robotic cars in the scale city and having a mixed traffic environment when you have connected automated vehicles interacting with human-driven vehicles. The vehicles have a small camera in front, so as you drive the car, you can see through the monitor what's going on in the traffic conditions ahead of you. So the camera is over here, if you can see. So this is another nice feature of the lab. We can also use it to have a cooperation of ground vehicles with drones in specific scenarios that we want to validate some of the team theory work that we do. We have built a digital replica of our scale city, and we can use this for our collaborators to sign in and do some experiments remotely. And finally, we have developed an app that you can replicate shared mobility, where you can, if you come to the lab, you can download the app and then you can call any of these little cars to come over to your origin, and then you can assign the destination. And then through this app, we can validate some of the optimization algorithms that we develop in the lab and see the eco-routing approaches. So there is an infrastructure, and at the end, once you have different origin destinations, you replicate some sort of traffic conditions, and then you can apply some of the optimization algorithms that we develop in the lab. The city was featured in the IEEE Control Systems magazine last December, make it in the front cover. We also have a driver simulation testbed with 6 driver emulators, and we use commercial software that can replicate any city that we want to investigate. So with this little introduction, let's get back to the technical work. So over the years, I have had the chance to work on different areas in transportation. I started with my dissertation where I developed the algorithms that can make the engine in a car to learn the driver's driving style and eventually optimize its operation. Then I moved on to hybrid electric vehicles and plug-in hybrid electric vehicles and developed power management control algorithms that can help us improve the efficiency of these vehicles. And over the last 13, 14 years or so, I've been working on connected automated vehicles and how we can use shared information to improve transportation efficiency and safety. So what I plan to do is I'm going to walk you through my journey, and as we go along, I'll highlighting several technical challenges, and then at the end of the story, have a lot of movies. So hopefully you have something to eat and enjoy. It's more entertaining. And then at the end, I will make the case about how we can combine learning and control. So my journey started in 2003 when I arrived in Detroit from Greece with 6 inches of snow, and I had to find a topic for my dissertation that will keep me busy for the next 5 years. So as I was reading articles, as perhaps some of you are doing as we speak, to find out an interesting topic for my dissertation, I came across some articles that essentially all have a common question. Why we cannot achieve the miles per gallon posted on our window sticker in the cars? So I thought that this is an interesting question that will keep me busy for the next few years, and I started digging into this. So when we buy a car, the car comes with a window sticker, right? And it says this is the fuel the miles per gallon fuel economy for your city driving, and this is for your highway driving. And although you can, most of the times you can achieve the fuel economy estimates for the highway driving, you can barely achieve those estimates for the cityway driving. So let's see why is this the case. To understand engine operation, we need to look at the engine operating domain. So you have a map of the engine, which is engine torque and engine speed. And these colorful contours called BSFC map, brake specific fuel consumption maps, and they give you fuel consumption per unit power. So the higher the value, the better the fuel economy, right? So as we drive the vehicle, this is the speed profile of the vehicle. As we accelerate, if you can look at the engine map, you can see a point jumping from point to point inside the map. And depending on how you drive and where's the point located, you have a corresponding fuel consumption map, right? Now, how we optimize engines? Well, the OEMs typically take the engine and discretize the engine operating domain, all this colorful map, with a finite, typically small number of steady-state operating points. When I say steady-state operating points, I mean constant torque and constant speed. And then they operate the engine at every steady-state operating point and compute the optimal values of injection timing, spark timing, all the variables of the engine. And then they have a big map. And they take this map and they put it in the engine control unit of your vehicle. So as you drive the car and you're going through different operating points, then the engine interpolates the values corresponding to the optimal points of the steady-state operating point, and this is how you operate the engine optimally. However, when I was a graduate student in Michigan, and some colleagues of mine did experimental work, and this is what they find out. If we operate the engine at the steady-state operating points, we have a constant fuel consumption. And this is why we get the estimates of highway driving, because the engine have been optimized. The engine have been optimized for steady-state operation. So when you drive your car with a cruise controller at constant speed, this is how you get the maximum fuel consumption. However, if you approach this operating point for a sequence of operating points, then fuel consumption will vary for a small transient period. And most importantly, if you approach this operating point from a different direction, then fuel consumption is associated with different values. So this is why we have the discrepancy when we drive in the city, because we drive in the stop-and-go driving mode in this regime, where the engines have not been optimized for. Now, how we can optimize the engine for all these different driving styles? Well, this is impossible, right? Because everybody drives different. So we can't really a priori optimize the engine for all these different sequences of engine operating points. So here's what I did for my dissertation. I took the engine and what I have learned in the control stuff, in the stochastic optimal control class, which by the way I'm offering next spring. They're called optimal control and decision theory. You might want to sign up. So I modeled the engine operating points transition as a control Markov chain. And then I learned the transition probability matrix as the driver drives the vehicle. And I showed that this probability matrix will converge to a stationary probability distribution, being characteristic of the driver's driving style. So as the driver drives the vehicle and we get a pattern of the engine operating point transition, then I learn this pattern, this pattern, and then I can derive an optimal control strategy that can optimize my controllable variables for these engine operating point transitions. So eventually the engine has a self-learning controller that learns the transition probability matrix corresponding to the driver's driving style and eventually learns to optimize the optimal calibration with respect to the driver's driving style. Now, if any other member of the family picks up the car, the engine can recognize that this is a new driver and start learning the driver's driving style for the new driver, and so forth and so on. So with this approach, we show that we can improve the efficiency of the engine by at least 80%, which is significant. By just doing better controls, you can improve fuel consumption by 8%, right? Eventually, Michigan get a patent for this dissertation, and I've heard that a couple of years ago they had some discussions to license this technology to a Silicon Valley giant who are working on the autonomous cars, and they want to have also autonomous powering systems. So Now, this is all the good story, but I promise to highlight the challenges on the learning part. Well, here's one challenge, because in this particular case, I start learning the transition probability matrix from scratch. And I'm applying some control, I'm exploring and exploiting what I have learned as I drive the vehicle. But I might pick, in the exploration phase of my reinforcement learning, I might pick up a value for the controllable variable for the engine that might stall the engine. And this is something that we cannot afford. You cannot really drive the vehicle and all of a sudden the engine stalls just because you explore a controllable variable which is, doesn't work. And the challenge now is that even if you, let's assume that you get the feasible domain of your action space precisely to avoid stalling the engine. If you take this feasible domain for a car designed in Michigan and you take it to Florida, this feasible domain will change. If you take this car to another state, colder or cooler or warmer, it will change. So the challenge here is that you can't really rely entirely on reinforcement learning, on making your system learn from scratch. You have to have a baseline, you have to have some adaptive control schemes that can make sure that you don't have undesirable outcomes. So that's the challenge, number one, right? Let's start counting. And then I moved to General Motors, and the first assignment in General Motors was to identify the fuel injection characteristic curves. So they have solenoid fuel injectors, and they wanted to use solenoid fuel injectors just because they were very cheaper, much cheaper from the piezoelectric fuel injectors. And so for the new technology that they were planning to work, if they go with the piezoelectric fuel injectors, which are precise, the business model wouldn't work. So I have to stick with a solenoid fuel injector. But as you can see here, I have 4 injectors with injector-to-injector variation in 2 different cylinder pressure. This is for 12 megapascal and this is for 20. So the 4 different fuel injectors means that if you have an engine with 4 injectors, then each cylinder, if you command the same pulse width, you get 4 different fuels inside the cylinder, which means that you have imbalances in the engine that can sacrifice fuel economy and emissions at the end. You have to have precise injection of the fuel inside the cylinder with a common pulse width. So my project was how I can come up with an approach that can learn these identification curves. And you might think that this is a very typical, easy problem, right? That's a curve, I have to learn, that's very standard. Well, here's the problem. In an engine, when I command the pulse width and I get the fuel, I cannot measure the fuel inside the cylinder. I don't have a sensor inside the cylinder that can give me the amount of fuel that I injected. So I don't have feedback, in other words. I don't even have air-fuel ratio on each individual cylinder. I have in downstream a central air-fuel ratio, right? So for me, essentially, it was a blind. How I can control a system if I don't have a feedback, if I cannot measure the output of the system, right? So eventually I combine a data set of that we have available offline, and I train a super a big neural network. But at the same time, I could not rely entirely on the supervisory on the supervisory learning with the neural networks. I had to attach some adaptive control schemes, and eventually you can see that starting from initial calibration, initially guess. These are the 4 true, hopefully you can see the 4 different colors of the injectors. The controller could identify the true injectors in a few cycles. When I say few cycles, that means few milliseconds, right? So by sampling within few cycles of the engine, few milliseconds, I was able to identify the 4 injector characteristic curves by combining supervised learning with neural networks and also adaptive control. So that's another, and of course, by doing so and being able to precisely identify the curves, you could be able to improve the fuel consumption for the engine by 4%, which is significant if we talk about, because this costs nothing. This is a piece of software that can give you 4% full improvement. Yes?
So what was the feedback or data that you were receiving to be able to do this?
So I had offline data that can give me pulse with fuel consumption, which are experimental data that they did of course, this data changes. So they have fuel injectors, and they tested these fuel injectors, and they collect data, pulse width, fuel amount. But this if you take this fuel injector and put it inside the cylinder with different temperature and cylinder pressure conditions, this changes. So that's why you cannot really rely entirely on neural networks. And then we had to do some adaptive control scheme on the fly just to make this work.
And the adaptive control on the fly was based on what information?
Based on the available signals that I have. Air fuel ratio, the central air fuel ratio. In the experimental and the demo vehicle that I have, I had also cylinder pressure. I was something, for each cylinder I had the pressure. So I had to sort of interpret, extrapolate this information.
I understand. Thank you.
And the most important challenge was the robustness in this case, because you can say that once the vehicle starts calibrating, you can sense the engine trembling or behaving in a certain way, and then you can smooth out. But in a production vehicle, you can't afford that. It has to be operating in an optimal way right away. And then after this project, I moved on to Oak Ridge National Lab and to another topic on power management and control for hybrid electric vehicles and plug-in hybrid electric vehicles. So let's see what is a plug-in or a hybrid electric vehicle. So in a hybrid electric vehicle, in addition to the engine, you have a motor, generator, and a battery that they can power the vehicle either separately or in combination. So as the driver presses the pedal position and asks for power, this power is being delivered through different combinations. You can have only the engine, or both the engine and the motor, or only the motor. And as you use the motor, you deplete the battery, right? So this is a scheme that you have the 3 dots corresponding to the 3 operating points: engine, motor, and the driver. So the driver is the black knot, and this torque demand by the driver is being given by the motor and the engine. As you operate the engine, you deplete the battery. This is the state of charge of the battery. So the state of charge of the battery goes down. And this is the vehicle speed profile. So as you deplete the battery, you have to make the decision at some point in a hybrid electric vehicle to charge the battery again. So you have to command the engine to power the generator to charge the battery. So there's a multi-decision making process, but eventually in order to address this, you consider the hybrid electric vehicle as a system with consisting of subsystems. And then the first step is to identify the feasible state and control actions pairs of this system. And then eventually you formulate a problem, which you will learn, some of you, when you take my class next semester. I'll keep advertising my class. So you want to derive the optimal control strategy that maximizes the efficiency or minimizes the losses of your vehicle, right? For any different driver. Now, to solve this problem in real time on board the vehicle, it's infeasible. You can't really afford this in a production vehicle, right? So, to address this and make it work, what I did, I reformulated the problem and formulated it as a multi-objective problem. So eventually I formulated a multi-objective problem that I want to maximize the efficiency of every subsystem. I solve this problem offline, and I derive a Pareto optimal set for any different realization of the driver. So I had the map of the engine, I had the efficient map of the motor. I put this in a big optimizer, formulated my problem, and solved it and created all the Pareto frontier that can give me all the trade-offs between all these subsystems. And then I operated, I took this map, put it in the hybrid electric vehicle, and operated by interpolating the Pareto optimal operating points. And I show actually in a result that if you do this, if you operate the system on this Pareto optimal operating point, then the average cost per unit time is minimized. The average cost per unit time means that you want to minimize the cost or maximize the efficiency in long term as you drive the vehicle for days, for weeks, and months. Anyhow, we did some simulation and we compare this approach, this solution, with reinforcement learning, and we got the same solution. So for the reinforcement learning, I mean, that was dynamic programming, but using reinforcement learning. For the reinforcement learning solution, we just took the model of the car and ran it again and again and again over the same driving cycle. And eventually, the system learned the optimal control strategy. And then to compare it with our approach, we ran the same model with the Pareto optimal solution in real time once, right? By interpolating the Pareto optimal control. And we got the same solution. We went further and we implemented this in a demo vehicle. we had an Audi plug-in hybrid electric vehicle, model 2016. That was part of the ARPA project that concluded a couple of years ago. So as you can see, we ran the model with the Audi's baseline controller that the vehicle has. This is the BSFC map that I mentioned before, and these are the engine operating points with the Audi's controller. And these are the engine operating points using our control approach. And you can see how the operating points has been squeezed to more efficient regimes. And given this operation, you were able to beat the Audi's controller by at least 12% in different case studies. So that was actually, this is actually in production, this code. Bosch was my industrial partner, and they have taken this into their portfolio, and they, that project we completed 3 years ago, so perhaps some of the new vehicles they might have this algorithm. So that was the case with power management control, but we use this approach. Yes.
Again, curiosity. Are any of these control strategies going to maybe in the future becoming destination aware, so you know what the sort of terrain is and where you're headed?
Yes, actually, I didn't mention in this project, the goal was to improve the Audi's efficiency by 20% by optimizing the powertrain, by also using connectivity and automation, which I will show you later on. So essentially, the car used information from the vehicles, used information from the infrastructure, and given this information, we improve the powertrain and also the speed profile of the vehicle by having the vehicle coordinate with other vehicles and avoid stop-and-go driving. We had also an eco-routing approach, which took into account what you said, all this, the route of the vehicle, and given that we could decide about the target state of charge of the battery, the optimal target. So there was a combination. The portion that I just showed you was just without using connectivity and automation, just the powertrain. But that was a very, and actually the partners of this project was University of Michigan, Boston University, Christos Kassandras, you met him, Oak Ridge National Lab, and Bosch. Bosch was the industrial partner. So the same approach, we use it in another project at Oak Ridge, when we have a vehicle, a building, and we have different renewable resources. We have battery, we have wind, and then the goal of this project was to distribute the electricity demand to different resources and make the building to be independent of electricity from the grid, make it an autonomous building. So in this project, we showcase that essentially we plug in an electric vehicle, and the electric vehicle we could use the battery of the electric vehicle to either charge the building or getting charged back to the, different combinations and different decision making that we have to do in this case. And then at some point I got involved with the connected automated vehicles, and the idea was how we can use connectivity and automation to avoid situations like this. If we have shared information from the vehicles, can we use this information to improve transportation efficiency? Actually, those ideas are not new. In 1939, that was the very first time that the sort of notion of automation was mentioned in New York's World's Fair Futurama, when they envisioned a world into the future, and one big portion of this exhibition was about transportation. And in 1939, they envisioned a high efficient transportation systems where all the vehicles can cruise with high speeds in a safe way. In 1956, GM featured the car 20 years into the future, and they showcased, sort of a car which is going to be a self-driving car. And they have a family driving to Detroit. This is the so-called GM Star. If you have a GM car today, they have the GM Star system. That's supposed to be this gentleman here. So the family drives to Chicago, and they get information about this gentleman, and then once they set up the routing, the car goes to a dedicated lane, and from that point on, the car is completely autonomous. And so imagine that this was a vision in 1956, right? I think this is the time that the car will go, and then the dad fires up a cigar. They want to show that with this kind of luxury and features in the car, you can enjoy a little bit and have some fun. We have ice cream and everything. Now, given the fact that we're still working on making this happen, it speaks to the difficulty and challenges of these problems, right? It's in 2023 and we're still having visions and dreams about getting these autonomous cars safely into the transportation. Anyhow, long story short, over the last few years, we were able to derive several approaches that can make the vehicles coordinate in intersections, in roundabouts, in merging roadways. So essentially, we collect information, and given this information, we do controls to coordinate the vehicles. So let me walk you through this process and how this works. I'm going to refer to an intersection, but the analysis and the exposition later on can be applied to any scenario that you want to consider. So let's assume that we have an intersection with 4 cars that are approaching this intersection. If this car continue crossing the intersection, then they will have some conflict at some point at the center of the intersection. The area that will have a potential lateral collision at the center of the intersection is called merging zone. And then we define the control zone outside this merging zone, inside of which the vehicles can talk to each other, can exchange information. So the problem is once the vehicle enters the control zone and gets information from the other vehicles and the infrastructure, how to cross the intersection without stop-and-go driving, without signals, without having any collision. So let's deep dive on this problem a little bit more. So I'm sorry about that. I clicked the wrong button. So if you consider we have the entry of the control zone and the exit of the control zone, the vehicle starts at the entry of the control zone, gets all the information from the other vehicles, and the idea is to identify the timing that they will be entering and exiting the merging zone to avoid lateral collision with any other vehicles, and also derive the optimal acceleration, deceleration given this time. So you have 2 problems. Find the scheduling of these times, entry and exit the merging zone and exit of the control zone. Once you find these times, then derive the optimal acceleration that can give me minimum fuel consumption. So if you think about it, eventually we're addressing 2 problems. The throughput maximization problem by scheduling the optimal timing that the vehicles will go through the intersection, and an energy minimization problem based on which, given the times, we want to minimize the acceleration and deceleration of the vehicles. So in our approach, we we model each vehicle as a double integrator, where P is the position of the vehicle, V is the speed of the vehicle, starting from the entry of the control zone. U is the control input, acceleration, deceleration, and S is the distance of the vehicle I from the preceding vehicle K. Now, somebody might argue, hey, you use a double integrator model to model a vehicle. That's a huge gap. And that would be a fair argument. And this is actually one of the claims that I will do later on about model-based control. Now, as I said, we're trying to derive the optimal control policy in real time. So we don't have the computational space to use any advanced models. So what we plan to do is to use the double integrator model to derive the optimal acceleration of the vehicle, and then we will use a low-level PI or PIT controller to track this optimal trajectory. So eventually, we translate the optimal control problem to a tracking signal problem. And this is how OEMs design cruise controllers as we speak. So that's the very basic model, and this is given the discrepancy of the model, mathematical model that we use for this case, and a real model of the car, which is multidimensional and very complex. Now, the next step is to define the feasible action set and state as imposed by the physical constraints of the vehicle. So for each vehicle, we have a maximum acceleration and braking capability. We need to capture this in our framework. And we also have a speed limit inside of which inside the control zone that the vehicles need to obey. Next, we take into account the safety constraints. We have the rear-end safety collision avoidance constraints. So essentially, each vehicle I needs to maintain a safe distance from the preceding vehicle. And also, we have a lateral collision avoidance constraints, which means that inside of the merging zone, we cannot really have 2 vehicles colliding. Once we do that, we formulate the problem, which is minimizing the L2 norm of the control input. Now, somebody argue, how come minimizing the L2 norm of the control input, acceleration, deceleration, can give us, minimizing the energy? Right? This doesn't have energy units. Well, if you remember from the first part of the talk, when we minimize the acceleration deceleration, we essentially minimize transient engine operation. We mimic the steady state operation. And this is how you get the fuel consumption benefit, right? Now, to solve this problem, we formulate the Hamiltonian analysis, right? And then if none of the state control or safety constraints become active, then we have a very nice closed form analytical solution where the optimal control is an affine function. The optimal speed of the vehicle is a nice quadratic polynomial, and the optimal position of the vehicle is a cubic polynomial. Now, if any of the state, control, or safety constraints become active, things are getting complicated. And in that case, what we need to do is we need to piece the constrained and unconstrained arcs together that can and solve a different problem. So just to give you a flavor of this, this is the case that none of the state, control, or safety constraints become active. If any of the state, control, or safety constraints become active, then you need to piece the constrained and unconstrained arcs to satisfy the Euler and Lagrange equations, and also the boundary conditions at the junction points T1 and T2. In T2, this will result in a set of algebraic nonlinear equations that you have to solve simultaneously using numerical methods, which means that the closed form solution that you had before is no longer the case. And it's also, this implies that you can really solve this problem in real time when you really need it. Anyhow, and of course, even if you get a solution, if you get lucky to have a solution, then a new constraint might become active, so you have to repeat this process. I think I have convinced you, but just to give you another flavor of the complexity, if, let's say, the safety constraints become active, this will impose some nonlinearities into the influence functions, and to address these nonlinearities, you have to adjoin the Lagrange multipliers with a partial derivative of your constraint with respect to the state, and this is the kind of set of equations that you have to deal with at the end. So you can imagine that this cannot really, you have to use numerical methods to solve this, which is not, you can't really afford this. Now, how to address this problem? How you can solve this problem in real time, avoiding all the cases that the state and control constraints or safety constraints become active. So we start with a solution of the unconstrained case. Remember, this is the cubic polynomial that I had when none of the state control constraints become active. If you look at this equation, we see that it is, first of all, a real value equation. It's increasing, and it's also differentiable, which means that this is a one-to-one function, which means that the inverse of this function exists. If we take the inverse, if we do Cardano's method for the cubic polynomial, and we take the inverse of this, the inverse function looks like this. This is a time, we call this time trajectory. So give us the time of the vehicle with respect to the distance, right? Now, imagine that once the vehicle enters the control zone, we have all the existing time trajectories of other vehicles inside the control zone. And looks something like that. Imagine that these black lines corresponds to time trajectories inside the control zone of all the vehicles. This is a vehicle going through the same path of our vehicle. These are the time trajectories corresponding to vehicles that crossing the intersection, and so forth and so on. So eventually, once the vehicle enters the control zone, what it has to do is to draw the time trajectory to avoid crossing any of the existing time trajectories. If we derive the time trajectory of the vehicle without crossing any of the existing trajectories, it means that we haven't activated any of the state, safety, or safety constraints. Right? Now, once I derive this, then if I inverse back, I get this equation. So eventually, by deriving the time trajectory and minimize the time, and then inverse back, I have solved both problems at the same time. I derive my time trajectory by minimizing the time that the vehicle will exit the control zone. I didn't intersect any of the existing time trajectories, so I didn't activate any of the state control or safety constraints. And then I inverse back, and I have this equation. This corresponds to the unconstrained case of my energy minimization problem. If I take the derivative of that, I get the speed. If I take the second derivative, I get the optimal control input, which is the affine function. Problem solved, right? So just to give you the mathematical, this is the visualization of the solution. Essentially, what we need to do is we start with this equation, and then we use the Cardano's method and we compute the inverse of that, right? And then we evaluate the inverse at the exit of the control zone. So essentially, you get the time trajectory, and then you have this time trajectory evaluated at the exit of the control zone, and you have the phi's, which are the coefficients, to shape the time trajectory. So by playing around with the phi's, you can minimize the exit of the time of the exit of the control zone and the shape. So eventually, this is your objective function now. Find, minimize this with respect to phi's. Of course, you have a bunch of constraints that you have to deal with. For example, you have to consider a bunch of quality constraints that's corresponding to the initial, final conditions and boundary conditions of the problem. Initial speed, initial position, final position, and so forth and so on. And you have a set of inequality constraints corresponding to the limit. Speed limit, the minimum speed at the entry of the control zone for the vehicles when they have to make a turn, and so forth and so on. By setting all these set of constraints, you come up with a nice problem to minimize the time trajectory evaluated at the exit of the control zone, subject to this set of equality and inequality constraints. And also, you allow the phi not to be part of the occupancy set. So essentially, for every lane, you have an occupancy set, which means which portion of this lane is occupied by other vehicles. So you want to avoid overlapping, getting a trajectory for the vehicle inside of a set that is already occupied. Now, the question here is, can we solve this problem in real time, right? Well, it turns out that the objective function is a convex function, and the set of equality and inequality constraints are affine functions. So if you apply the Slutter's weaker condition, then you can show that there is no duality gap in this problem, which is a nice feature, and it's a nice indicator that we can solve this problem in real time. We apply this approach to different scenarios, including intersections, merging roadways, corridors. Let me show you some results. This is an intersection in our scale city. Every vehicle gets into the control zone, start deriving this optimal time trajectory that I mentioned, and you can see how the vehicles can cross the intersection without stop and go driving, without congestion. There are some delays in the. There's a smooth split. The delays comes from the Zoom, not from the video. This is another case when we have a corridor. So we have about 16 vehicles here crossing a roundabout, the intersection, and an emerging roadway. You can see how all these vehicles, derive the optimal trajectories and going through these scenarios without stop and go driving and without having any collision. We also developed this in our demo vehicle. That was the second part of the project that I mentioned. So we went to University of Michigan M-City. In M-City, they have the augmented reality, so you can have a physical entity, the car, into the testbed, and then you have a bunch of virtual vehicles interacting and broadcasting with a real vehicle. So as you can see in this scenario, this is the baseline scenario. No connectivity, no automation. And this is the scenario when the Audi drives with our control algorithms. So you can see the Audi alone in the field, but then all these black vehicles are virtual vehicles broadcasting with the Audi. So these are the guest vehicles inside the field. So as you can see, as the Audi approaches the merging roadway, these are the black vehicles that broadcasting, and the Audi coordinate with these black vehicles and get into the merging zone without stop and go driving, right? In this case, there is this black virtual vehicle that blocks the Audi and essentially waits until they find a good spot to merge in. So this is it's also replicate the real scenario, but instead of having multiple vehicles, you have virtual vehicles. And this can give you a little bit of less headache on safety constraints because you have, and of course you can replicate these experiments all over again if you have virtual vehicles because you can identify the initial conditions. We also put the Audi in a chassis dyno in both facilities. So this is what you're gonna see here is the baseline scenario without connectivity automation. On the right is the scenario when the Audi drives with our control algorithms. So we put the Audi on the chassis dyno, both did that, and then the Audi drove through a virtual scenario. This is the speed profile with a baseline scenario. You can see that we have stop and go driving, just because the driver have to come to a full stop in scenarios that they have potential conflict. This is the scenario without control algorithms. You can see that we have eliminated this stop and go driving, right? is like driving in a freeway. If you eliminate this stop and go driving, essentially you get different benefits ranging from 30% all the way to 34%. Now, if you think that these values are high, go ahead and compare the fuel economy that you have on your car for the city driving and the highway driving. If you do the comparison, that's the kind of benefits that you get. Because you essentially, instead of driving in the city, you're driving in a freeway. So we've seen different methods, and I'm going to conclude with that. And we see model-based control approach with a coordination of vehicles. And you've seen that we use a double integrator model. So eventually we have a discrepancy between the model and the real vehicle. And then in order to address this, once we derive the optimal control input, we have the PI or PID controller to account for that. In the scenario with the engines, we use supervised learning with neural networks. But again, we couldn't rely entirely on the data offline. I had to do some adaptive control. In the reinforcement learning example with the engine, I showed you that there are robust concerns if you let the car drives or learns the optimal calibration from scratch. So the idea is, can we combine both learning and control, right? Now, in our approach, what we do essentially, let's say that we have an actual cyber-physical system. That's our real system. We have some disturbance in the system. We have some noisy outputs, right? We get the output, but there's some noise, some errors from the measurement. And then what we want to do is to derive the optimal control strategy to optimize the operation of the system. Now, let's consider that we have also a model, any simple model of this system. And you operate this model in parallel. So under the same input, under the same disturbance, and you have some sort of measurement noise. Then what we do essentially, what's the key idea is to establish an information state. And this information state includes information from the state of the actual CPS and also the state of the model. And then if you can show that with this information state does not depend on the control strategy of the system, then what you can do is you can use the model to derive offline this control strategy parameterized with respect to the information state. And then once you implement this control strategy, you just learn the information state. There's a little bit of more details on that. I'm going to skip the discussion just for the sake of argument, and I see that you guys look tired from all of that so far. So I want to have some time for questions. So I'm going to wrap up by saying that eventually, with this approach, you can derive, using your model, you can derive the control strategy offline, parameterized with this information state. And then once you start implementing this control strategy, you derive data from both the actual CPS and the CPS model, and you can start learning the information state. Once you learn the information state, the policy that you derive offline for your system becomes optimal for the actual system. And this is an approach, we're trying to implement this in different applications related to emerging mobility systems. We believe that this approach can be useful in cases that you have a system where data coming to the system in real time and not altogether in advance. So any of the standard approaches can be difficult to apply. So with this, I would like to thank you for your attention. I'd be happy to take any questions. Yes.
Intersection crossing problem. How do you address like the priority of the vehicle? Suppose a fire truck or an ambulance is passing.
We don't impose any priorities, simply because we did some studies to find out that if you can prioritize on, let's say, a fire truck, you cause more problem rather than solving the problem. If you let the system goes, since you don't have stop and go driving, it's better off for everyone just to go as it is, right? So we did some studies and we tried to prioritize to some ambulance or fire truck because the solution was worse off than just having the vehicles crossing the intersection without any priorities. If you think about it, if you have free flow, right, just let it go.
So this is great. So for the control, of course, there is this multi-layer
from the powertrain layer all the way to vehicle interaction control and the system level control. In doing all these control studies, did you ever come to a point where you feel there is actually a limit to things that we can control, such that you will say, "Oh, I'll just give up control instead. I'll let things." So, have you come across?
Yeah, that's a great question. Yes, indeed, and this happens essentially in any scenario, traffic scenario. You have some given capacity, which you cannot repeat. So once you start getting too close to this capacity of the roads, then there is no control. The controls are saturated. You have in the fundamental transportation diagram, once you cross this tipping point, then eventually you have, the only thing that you can do is that even you increase the control zone so that you can have more time for vehicles to coordinate, or you increase the speed limit so that you can rush the vehicles through the intersection or other scenarios. But both cases have limitations and safety constraints. For example, you can't really increase the speed limit of the vehicles. That's not ideal. At the same time, you can't really increase a lot this control zone because there are limitations on how far away the vehicles can communicate. So, indeed, there are limits. After you hit these limits, then there is nothing more that you can do. You just, well, there is one approach, and what we start doing is that we try to reroute some of the vehicles crossing the intersection. So when you see that the intersection is getting busy and you're reaching the capacity of the roads, then start rerouting some of the vehicles to go through other routes, avoiding this intersection. So we're trying to combine the eco-routing approach with a low-level coordination. So that's one way to do that.
Thank you.
Questions? Maybe I have a very high-level
Sure.
question. Like you said that these autonomous driving was like first conjectured in the 50s. Like, where do you think we are? Like, is another 20 years this is going to happen, or do we need another 70 years?
Well, no, I think we have made progress. The main challenge is the human in the loop. This is so. If we assume that we have only autonomous vehicles out there right now, I think it would be fun. We have the technologies to do that. But once you put a human in the loop and you have a human driving vehicle or a pedestrian or somebody interacting with this, then this is how things getting complicated. And there's also another dimension of the social dimension and ethics that goes with it, and legislative aspects that make a little bit complication. For example, if you have an autonomous vehicle and you have an old woman and a little child that you might have the dilemma to hit, what do you do? How do you call that? What do you do? What do you hit?
Brake.
You hit the brake, exactly. You hit the brake. That's the easy question. But of course, what I'm trying to say is that there are different dilemmas that as people instantaneous do, but you can't really code this. This is not so there are ethics and other non-engineering related issues.
And other people working on
And
this?
there are, but here's the problem. The problem is that once you build up multidisciplinary teams, and you reach out to funding agencies for this, it's really hard for them to see you might have only engineers in the panel or only social scientists, and it's hard to find that. There is no single easy path to get to this problem by getting different disciplines and different expertise. This is a multidimensional problem, and that's the kind of sociotechnical system approach that you need to take. If you can combine engineering with institutional dimension and social dimension, we have policy scientists, have social scientists, and so we to answer your question, we get technologically. I think we are made a lot of progress, but there are the other aspects that we need to integrate so that we can push this out and make this part of our life.
Okay. Great. So if there's no more questions, thank you again to our speakers.
Thank you for having me.